And thank you all for still being here. I know these are long days, and actually the lectures are really fantastic and so much information that you are getting. So let's try to get a bit more. Yesterday you did very well, and you were asking a lot of questions. Please keep asking a lot of questions. That's the goal of this, that you understand, that you learn. We don't need to go that far, but it's important that every step you are on the way. Okay? Just maybe to refresh our minds from what we were seeing yesterday. So we were, well, first I was making the argument that gravitational waves are really unique probes for cosmology. But then we were studying in more detail some of the basic properties of these waves. And what we the way we define these gravitational waves were as these linear perturbations, these small perturbations of our background space-time metric. So we were making this decomposition of the metric of space and time in a background and some perturbation where the amplitude, we were saying that it was small compared to the amplitude of the background. And then we took this ansatz and plug it into Einstein field equation. So we put this into GR. And then we were obtaining a very important equation which tells us the propagation of gravitational waves in a curved spacetime. So box h mu nu plus 2 times the Riemann tensor of the background coupled to the perturbations. And we saw that this equation is very interesting because it has couplings of the background metric to the gravitational waves through the box operator. This is the contraction of the covariant derivatives. And then potentially more phenomenology comes from the coupling of the gravitational waves with the Riemann. Though what we found is that in the limit in which the length scale that defines the background, when this length scale is much larger than that of the gravitational waves wavelength, then actually this term didn't play a role. And then the geometric optics propagation is actually very simple and completely analogous to that of electromagnetism. So we were seeing that gravitational waves, they propagate in null geodesics. So this is these first 2 equations that I'm writing here. And then we were finding as well that the gravitational waves are conserved as they propagate in vacuum, and that can also be re-expressed as this conservation of gravitons. We had some discussion about that. And also importantly, the fact that that the polarization tensor is parallel transport, which is this equation here, which means that it does not change as it propagates, and also that when we are in the Lorentz gauge, that it is orthogonal to the propagation. So, and here I should, I guess, add the division that we were making. We were building this h mu nu with some amplitude, some polarization tensor, and then some phase, and then the wave vector is just the derivative of the phase. So these are the basic properties of the gravitational waves. And then we end the lecture yesterday by discussing, and this has come again in the question session about the number of degrees of freedom, which gravitational waves are described by 2 degrees of freedom, and we will work with the H plus and H cross polarizations. I was just looking actually because I was thinking that I knew somewhere where this discussion of the number of degrees of freedom is well explained in terms of in the presence of matter. And actually there is a review paper by Flanagan and Hughes, from 2005. I think it's called The Basics of Gravitational Waves or something similar, where actually they do the composition of the different modes in the presence of matter, and then they saw that only the tensor modes are actually propagating. So maybe that's a good reference for you guys. Are there questions related to what we saw yesterday, more than what has been asked already? But since we have the equations here. No. Okay, so what do we want to do today? What we want to do today is these are the properties of the waves as they propagate, but we want to understand how they are generated, and in particular, the system that we are going to have in mind. Our goal is to study this coalescence of compact objects that are going to orbit around each other until they merge. So if we want to study this system, what we need to understand is how gravitational waves are sourced by matter. So we want to study the gravitational wave generation. And for this matter, what I will be doing as a simplifying assumption in the beginning is to consider, I'm going to consider a source in flat space. And then tomorrow, we will see how this can be extended to the case of cosmology, although I already alluded today in the Q&A that if you are in cosmology, actually it's very easy because you can always go to the reference frame where you can always change to conformal time, and then you can re-express things in the same way. But when we have a source in flat space, then the equation that we need to solve is the box operator of I don't know what, this is not writing properly. Yeah, the box operator in flat spacetime, which is nothing but the contraction of the partial derivatives acting on our h mu nu. And then what we are going to have is the presence of some energy momentum tensor. So at the beginning, I'm going to be general. I'm not going to specify this energy momentum tensor, and then later in the second part of today, we will specify for actually 2 compact objects that are merging with each other. Something to notice as well is that actually one can go a bit more general than this, and actually you can take, if you want, actually your nonlinearities from the theory, and you can actually define an effective stress tensor, tau mu nu. This is an effective stress energy tensor that actually can include some of the nonlinear effects. For the purpose of what we are going to do today, actually everything is going to be, we're going to be focused on the situation in which the binaries are far away and they are moving not so fast. So this is not going to be relevant, but just so that you know that actually the formalism can be generalized, and that's something that is useful. And then in flat spacetime, the Lorentz gauge condition would be simply the partial derivative contracted with our perturbations. Of course, also the perturbations themselves, these trace reverse perturbations, they are as they were defined before, but now our background metric is the Minkowski metric. I just write it here for completeness. But what is interesting is that if you take this gauge condition, actually what you can show is that if you apply a box operator to this condition, h mu nu bar, which this is 0 from this equation here, because these are all, this is the box operator in flat spacetime. These are all flat, not fat. These are all partial derivatives. So actually, they commute with each other. So one can write, one can take the partial mu outside and then get the box h mu nu there. And then if you take this equation, you just plug it here. And then what you find, minus 16 pi g, partial derivative of t mu nu contracted. So what we have found here is that from this condition and the fact that these equations of motion are satisfied, we can also see that the energy momentum tensor, and I'm going to write it here so that it's big and you can see it, the energy momentum tensor, it's also going to be conserved. So this is the conservation of the energy momentum tensor. Yes, I see one in the back and then here. Sorry, first I think it was. It's conserved in other gauges. It's a consequence of the theory, which is the mostly our equations of motion here. Yeah. Sorry. Yes. Under here? No. So this is the definition. I think this is correct, but sorry, maybe I'm. No, sorry. Yes, I apologize for this notation, but so this bar is the trace reverse. Sorry. Yes, now I see your confusion. That I'm using bars for backgrounds and for the trace reverse. Sorry, I apologize for that. Yeah, this is just a definition that you are taking out this element from the perturbations, and that's useful because when you have this variable here, then you don't have traces in the equations here. Alternatively, you could not include the bar here, and then you will have traces of the energy momentum tensor. But this is useful for that. At the end, actually, when you focus on the transverse and traceless gauge, you don't care because the trace is 0, so then they are the same. So that's, but here, before doing that, then this is the general part. More questions? Okay, so great. So we have an equation, and then we also have some conservation loss here. But actually, this equation here, is one of the few that we do know how to solve, because we can solve this using the Green's function, which probably you have all encountered at different stages. Solve the equation using the Green's function method. Green's function method. So the Green's function method tell us how to solve an equation in which you have a function of this type. You have the box operator, which is sourced by a delta function. And then for the flat spacetime D'Alembertian operator, then the solution of this Green's function, it's given by -1 over 4 pi, the modulus of x prime minus x, x minus x prime, delta t prime minus t retarded, where the retarded time is defined as t minus the modulus of x minus x prime. So here, and I have to, these are not bars, this is the symbol of vectors. So these are, what I'm referring here is I'm decomposing the 4 space-time dimensions into time and space. So what the Green's function tells you is how you can find this solution in terms, and it has been reduced only to a delta function in time. But the important thing here is that the time that the signal is sensitive to is not the time itself, but is you have to subtract some vector. So here the situation that we have is that we have some source of size r, and then we have some point here x, and then we are looking at points x prime within the source, and then this will be the difference of x minus x prime. So we are finding the solution, which what is telling you is that actually to get the information of what is happening, you need to wait for the information to come, and then it travels at the speed of light. So this is the term that is accounting for that. So it's a way of preserving the causality of the system. Right. So if we take this solution, and we specialize for this equation, then what we have is that we can actually formally write directly the solution for the gravitational waves which are generated, which depend on time and x, and this will be 4 times g, and then this is an integral over d3 x prime, and then one has tau mu nu t minus the retarded time, sorry, the retarded time itself, also depends on x prime, and then this is divided by x minus x prime. So this is the formal solution that tells you how gravitational waves are sourced. And here, of course, this integral goes into the volume of the source. And that's because when you are outside, so this is outside, the T mu nu is just 0. Okay? Yes, please. 4G, sorry, yes. Yes. Please keep asking about migrating. It's, I know it can be challenging. So, okay. So it's more or less clear the logic until here? Okay, so what we want to do now, yes, sorry? Sorry, this is the volume of the source. Yeah, I don't know how to, yeah. It's just, I'm just saying that if you don't need to integrate outside of the source because then the energy momentum is 0, so then you don't have anything here. Yeah. Yes? Okay, so we want to look at the solution for a distant observer. So we want to be in the what is called the far zone in the gravitational wave community. So we want to look at an observer which is far away from the source. And here I'm defining the position x as some modulus r times the vector, the normal vector n. So we want to look for how the signal that would be observed for someone which is far away. And if someone is far away, what we can do is that we can expand at far distances. And what this means in practice is that we want to take this x minus x prime, and then we can expand it as r minus x prime times n, and then we will have terms that will be of order, of higher order. And here this x prime n graphically would be this this element there. Okay? So we want to look at distances far away, and then we make that expansion, and then we look for the solution, the leading order solution. And that will be if we take our previous expression here, and then here by the, well, let me write it and then I comment. So we have Tx for G, R, and then we have the integral x prime tau ij T minus R plus x prime times n x prime. So what have I done here? So I have done two things. First, I have taken the exponent, sorry, the denominator here, and then to leading order, this is going to contribute to an r here. So this is coming from the x minus x prime. And then I have also expanded the retarded time. And then finally, I have also said that as we are actually far away, the only components that we care, because we are in vacuum and far away, are the spatial components. So we have that h mu nu, h mu 0 is 0. Okay? So this is an improvement because we have already simplified this term here. but actually we still have some complication because we need to deal with this integral that you see here. We have the dependence of x prime within the time and also here in the positions. So we need to do something else. Is it clear until here? Yes. Please. N is the direction of the position. Yes. More questions? Yes. IJ. So the one thing is that I'm just already moved to spatial components only because the temporal ones are 0. Yes. Confused about what? Okay. Yes. Yes, good question. It was more of a formality just because some people, when they study actually different formalism, like I just wanted to say that if you are interested, you can include some of the nonlinearities in this effective term, and actually the equations follow the same because this is also conserve, this effective stress tensor. Now, it's not relevant actually for our discussion, but it's just, yeah, it can be useful for when people study, for example, the post-Minkowskian formalism that tries to go a bit beyond what we are going to do here. That's relevant. Yes, please. Uh, Here? No, sorry, where? Yeah, please, yes, yes. Indices are important. I see 2 questions here. Right, so this is something that you can, so you have the freedom to, you have the freedom to eliminate these residual modes, and that's something that is a choice that you make. It's a gauge choice. Just you want to go from these 10 components of the metric perturbations to just the 2 physical degrees of freedom, and that's a useful choice. Yes. Great. So when you are in flat space, you don't care. You can go up and down. But yes. Yes. Y- Sorry, is a what? This term? No, so actually, what we want to include that because that's gonna tell us something about the source itself. So that's actually what I'm gonna explain in a second. I think there were more questions. No? Yes. Yes. No, sorry, no. Actually, the Green's function method is a way that you have to solve the flat space-time, this type of equation. So this method is about this type of equation having some source, and it's independent of here what I have in here, what is my source. Um, I see what you mean. No, but Let me not enter into that, and we can follow up later. Yeah, thanks. Yes. This is x equals to r times n. This is an r, yes. Yes. Great. I love how many questions there are. More? Are there more? No, please, please. I'm not joking. Yes? Right. So this is what we were seeing yesterday at the end of the class. So we have this h mu nu is a symmetric tensor in 4 space-time dimensions. So this gives you 10 components in general. And then you need to see how you reduce those. So when you choose the gates, as we were doing, these Lorentz gates, you are eliminating some of the 4 of the components, but you still have another 4 that are residual gauge freedom that you can fix in different ways. And it is convenient to it's a convenient choice to eliminate the temporal component so that you can solve the equations in a more easier way or interpret the equations in a more easier way. But this is a choice. You could make a different choice and you would have to solve it taking that into account, but the observable should be the same. It's just that this is easier because then you are seeing in some way the effect of the gravitational waves as changing the spatial components only, propagating in a given direction, and that's, I guess, conceptually easier to deal with. Okay, now I'm going to stop for a second the questions because I need to continue, but just so that it triggers more questions. Right, so where can I erase? I'm going to erase here. So we have this general solution, and then we are going to make a further assumption. So at the moment, we were just looking at the gravitational waves that are far away, and we arrive at this expression over here. And now we want to see how to solve it. But then what we are going to assume is that actually, let me write it again, that this source that we have is going to have components which are moving at low velocity. So we are going to do a low velocity expansion or a non-relativistic expansion. And that's going to help us to get an analytical solution. So within the source, the velocities within the source and in our more simplified picture of the source, this is a source of scale r. The velocities are of the order of the orbital velocities times r. And then we have, on the other hand, that the radiation frequency is of the order of the orbital frequency, and this is something that we are going to see in more detail today. And this is proportional to B over R. So from here, we have that the wavelength, the reduced wavelength, which is just C over the omega, this is going to be proportional to C over B times R. So what this means is that if we have sources in which the velocities within the source are small compared to the speed of light, then what this happens is that this number, this wavelength, is going to be much larger than the size of the object. So what this means is that in the low velocity expansion, we need to require that our wavelength is much larger than the size of the object. And when you are in this case, this is useful, this regime, because it can be understood analytically, because when you are not so sensitive to the inner structures of the source, then you can define your source doing a multiple expansion. So in particular, we can take our energy momentum tensor, T minus R plus X prime times N, which is also a function of X prime. And we can do an expansion here. We can do an expansion. Around X prime times N. So if we do this expansion, the first term that we have there is actually what was being asked, which is when you are far, you get this T, minus R, this T minus R, X, and then the first term that you get derivative of time, tau KL, and then, sorry, why I have KL? No, IJ, this is IJ. This is IJ. Tau IJ, X prime times N. So what I'm doing here, if you haven't noticed, is just a Taylor expansion. So I'm taking this expression and expanding around when this value is small. So I have to take derivatives with respect to time and then multiply by the small difference. And then one would have the quadratic term, which is the T tau KL, sorry, JL, not KL, tau IJ. And then we have X prime, X I, X prime, X K, X prime L contracted with N K and N L. So here, what happens is that every time that you go to a higher order in the Taylor expansion, then you get another term of X prime times N. So this is why I'm contracting these indices there. Just a second. So the important thing here is that the time derivatives that we have, every time you have a time derivative, you have something which will be of the order of the frequency. And then when you have this X prime, will be of the order of R. So what you see is that actually this expansion that is doing every time is of the order of B over C. So every term, when you are doing the low velocity expansion, is going to be more suppressed than the other one. There was a question. Yes. Because this is the time component, is that you are expanding around. Yes. Yeah, thanks for that question. Yes. Yes. Sorry, yes, that's probably the confusion is because here I'm referring to the velocity of the source. So this V is it tells you about the relative velocity of the source. itself, not the waves that it's generating. Does it make sense? So you have imagine, let's go to the concrete example of two black holes. This is referring to the velocity of the black holes, which is different from the velocity of the waves that they generate. The velocity of the wave is always the speed of light, as you are correctly pointing out. Yes, actually from here, the fact that they follow null geodesics, that tells you that they propagate at the speed of light. So the gravitational waves, they propagate at the speed of light, and then the sources that generate them, they propagate at the speed that they can. Actually, interestingly enough, when the black holes are about to merge, they are almost at the speed of light, which is actually pretty impressive if you think of like have astrophysical objects of tens of solar masses moving almost at the speed of light. But actually, that's not the regime that we are studying here, where we can get analytical results. To get analytical results, you have to be in a regime in which the black holes are a bit far away, so that they are moving at a fraction of the speed of light, so that then we can do this low velocity expansion. Because what we are seeing here, which is very useful, is that it's telling us that actually we can neglect, we can forget about this here, and then this is going to be much simpler to solve. Yes? Sorry, perhaps. What do I'm saying? I'm saying here that, yes, this is not matching. No, sorry. Sorry. What I meant is that this term is of the order of r, the derivative with respect to time of the order of the frequency. And then what this means is that that you are gonna, so that, where do we have it? Yeah, so that from here, that each of these terms is gonna give you a correction of the order of b over c. Because you have, if you multiply this here and you move this there, then you have, yeah, so that's what I meant. Okay. So then we are almost there, actually, to get to a very important results. And to get to that important result, actually what we can use is we can use the conservation of the energy momentum tensor that I erased there. Where should I write it? I'm going to write it here. Because and this is something that I'm not going to derive in detail, but it's actually something that you can do yourselves. It's a good exercise of partial derivatives and chain rules. But you can show actually that there is from this conservation of the energy momentum tensor, one can find this relation that the derivative with respect to the zero component of xi, xj times tau 0, 0, it's equals to partial derivative with respect to k, partial derivative with respect to L, xi, xj, tau kl, minus 2, partial derivative with respect to k. It's a bit long, but you will see that we don't need to worry about most of the terms. xi, tau jk, plus xj, tau ka, and then finally 2 times tau ij. So this is a long expression, but actually why it's useful for us is because we have here this tau ij, that you see this tau ij is appearing in that integral. So what you can do is that you can re-express this tau ij in terms of all these derivatives of the energy momentum tensor. However, what you can see here is that you have derivatives here with respect to space, and here you are integrating over some volume. So these terms, these two terms are boundary terms. So when you integrate, when you put them in the integral, they will give you the value of these functions at the boundary, and if you and those actually those boundary terms they because we are in vacuum, they vanish. So what this means is that actually we can rewrite this integral there, and we can change this tau ij in terms of second derivatives of this element here. So the expression that we arrive at is the following: 2g divided by r, and then we have the second time derivative of this quadruple moment that I'm going to define in a second. That is a function of the retarded time. So that's the equation, and then the quadruple tensor. It's defined as the integral over dx d3x of tau 0, 0, xi, xj, and this one can relate to the to the energy density of the system, Tx, xi, xj. So, and there is no. So this result here, what is telling us is that gravitational waves are generated by accelerated quadruple mass moments. Yes. Yes. This is little r. Yes, because you are looking for the signal that the observer would see. Yes. Sorry, it's because I'm sorry, I'm using c equals to 1. Yes, sorry, yes. Yes, that's my inconsistency. But it's sometimes you need to put the c's because otherwise it feels weird. But, well, I don't know. Maybe I should have just not put any c's, but yeah. Okay, but this is a very important result. The fact that at leading order, the leading order contribution to the gravitational waves come from the acceleration. You have second time derivatives of the quadruple mass moment. So that's the leading term. And then, of course, the other thing that you see here is that also our waves are going to scale inversely with the distance, which for the question of cosmology is actually very important because that's where it's going to come. We will see tomorrow that you can obtain their information for cosmology. Sorry, accelerated quadrupole mass moment. So the quadrupole mass moment is this MIJ, which is essentially comes from the energy density, but is the quadrupolar component. If you have like the dipolar component, that's just telling you about the center of mass movement, and that doesn't generate gravitational waves because it's conserved, and also the energy itself is conserved, so it's not doesn't generate. Yes, so that's so. What we are going to see now is an example of how to compute the quadrupole mass moment for a given system, and then you will see the waves that you get. Yes. So when no, so sorry. So the fact that you generate gravitational wave from accelerated sources, that's general. So that's what you, in the early universe, if you have things which are accelerating and changing, that's going to generate gravitational waves. But the fact that you are dominated by the quadrupole moment comes from the low velocity expansion. Yes, which is very useful because, as you will see now, then it means that you can get analytical results for concrete examples. In general, this low velocity expansion is going to break down because, as we are going to see, like these black holes or these neutron stars, I mean, they are orbiting around each other and they are losing energy, so they are getting closer and they are moving faster, and they are losing more energy and they are moving even faster. So this low velocity expansion is meant to stop being valid at some point, but actually serves to give some physical understanding in a wide range of times or frequencies. Okay? More questions or sorry? Okay, so what we are going to do now for the rest is we want to focus on specifically in spiral of compact objects. And essentially, what we just want to do is to put into play this quadrupole formula. So we want to define a system in which you have two compact objects that we are going to model actually as point masses, and we want to see what's the gravitational wave that you generate. So we have a system of 2 point masses, which are defined by M1, which is located at position R1. So M1 located at a position R1, and then we have M2, which is located at a position R2. And because these are point masses, then they only contribute to the energy density at the given point. Okay? So for this system, the quadrupole moment is easy to compute. You just need to take this expression and then you plug it here. Because these are delta functions, then you get directly that the quadrupole mass moment is given by M1, and then you have R1I, R1J, and then you have M2, and you have R2I, R2J. Okay? And then what is useful now is to go to the reference system of the center of mass. And then if you do that, then this is defined as the total mass times the R of the center of mass I that I'm going to define in a second, R of the center of mass J, and then you have the reduced mass mu times Ri Rj. So here, in this expression, we have that the center of mass R is M1 R1 plus M2 R2 divided by M1 times M2. And then we have R, which is the difference of R2 minus R1. So this is R. And what else I need to define? Yes, so the total mass is M1 plus M2. And then the reduced mass is M1 times M2 divided by M1 plus M2. And why is it useful to go to the reference system of the center of mass? Well, this is useful because if you have a system that is isolated, then the center of mass does not accelerate. And if it does not accelerate, it will not produce gravitational waves. So actually, when you have isolated binary, what we have is effectively, we have an effective one-body problem. So we have reduced the system, and we just need to follow a particle which is of mass mu. Does this sound familiar, more or less? Okay. So with this, what we so we have the quadrupole moment, but then we need to compute the the second time derivatives, and what we are gonna need to make some choices. So this this effective one-body problem can be described as the most is restricted to the motion of an orbit in a plane. So we are going to choose that plane it's in the x and y plane, so that the orbit is confined to that plane, and then we are going to choose the to parameterize this orbit that is going to be a circular orbit to be r. This is the now is the radius of the orbit with some frequency and then some phase. Sine omega s t, and then we don't have anything in the set component. So as a first step, what we are going to assume is that there is no back reaction. So we assume that R is constant, so there is no back reaction, and then we will later relax this. But at the beginning, we say that there is no back reaction from the gravitational wave emission. Okay? So we have the coordinates here. We have that the quadrupole moment in the center of mass. It only cares about the the reduced mass. So then we can just compute derivatives in this system. First of all, we just compute. We put these choices into the definition, so that we have mu r squared 1 minus cosine of 2 omega s t. And then we have m22 as a function of time. We have mu r squared 1 plus, so here is minus, this is plus. And this is just, I'm just using some trigonometric functions to go from cosines squares to cosines of 2 times the phase, and here I'm missing divided by 2. And then 1/2 m1, 2 as a function of time is the same as the 2, 1. And this is minus 1/2 of mu r squared sine of 2 omega s t. Okay? So we have now a concrete expression for the quadrupole mass moment. And then what we need to do is we need to take time derivatives. So I'm going to do it here. So if you take 2 times derivatives of this expression, what you find out is that the second time derivative of the 1, 1 are equals to the negative of the 2, 2. And this is equals to 2 mu r squared omega s squared cosine of 2 omega s t. And then the other 2 components, 1, 2, the second time derivative is equal to the second time derivative of the 2, 1. And then this is 2 mu r squared omega s squared sine of 2 omega s t. So we have the expression here, and actually the only thing we need to do is to just plug that second accelerated quadrupole moment to obtain the Hij for the case. So the Hij would be 4g r squared omega s squared divided by r, and then I have cosine, and I'm going to write it in a matrix form. 2 times st sine of 2 omega st 0, and then sine 2 omega st minus cosine 2 omega st 0, 0, 0, and 0. So this is the expression that one gets for the gravitational waves which are emitted by 2 point particles which are orbiting around each other. Here, there are 2 elements which are important. First is that you see that the frequency of the gravitational waves is 2 times the orbital frequency. And that comes actually precisely from the fact that it's the quadrupole moment which is sourcing the gravitational waves. And then the other thing that you can notice is that H plus and H cross So H plus is here. This is minus H plus. This is H cross, that they are dephased. They have the same expression, but they are dephased because one goes with the cosine and the other goes with the sine. But for the rest, actually, they have the same behavior. So this is very important, and this relates to what I was saying yesterday, that the gravitational waves, they have frequency, they have wavelengths which are of astrophysical size, and you see here directly that this comes is 2 times the orbital frequency, and that is of the size of the orbit. Yes, please. Yeah, so this is transverse and traceless. Sorry, that was the question? Yes, yes. So, yes, so because this is already traceless, actually it's the same. Yeah, thanks. More questions? So, actually, from this expression, there is a very important quantity that actually arises from this expression, which is a combination. So you see here that you have R and then frequencies, but actually we can re-express these elements in terms of the masses. So if we define this new variable, which is called the shear mass, this shear mass is a combination which is strange, but is the reduced mass to the 3/5 times the total mass to the 2/5, which is also equals to m1 times m2 to the 3/5 divided by n1 plus m2 to the 1/5. This seems like a very weird quantity, but actually, if you use the fact that the orbital frequency is related to by Kepler's law, gm dot divided by r to the cube. If you use this expression, and then you plug it here, actually what you find out is that the gravitational wave amplitude for the plus in part is the same for the cross. It's going to be 4 times divided by r, and then you have g shear mass to the 5/3 times pi to the gravitational wave frequency to the 2/3, and then you have the cosine of 2 pi f times t. So actually, and for the cross, is the same, but you just need to change the cosine by a sine. What you see actually is that the shear mass, this combination of masses, is the quantity that controls the amplitude of the gravitational waves at leading order. And that's why this quantity is actually of great importance, because it's the quantity that observationally we can constrain the best, because it's the one that appears at leading order. You can do yourself the math of just putting this definition here, and then you get that there. Yes? Yes, it's because this is the leading term that defines the wave. So it's if you want, is the most important contribution to the wave. And you see that it's only defined, at least for simple system, it's only defined, at least the amplitude from the shear mass. And we are going to see in a second that the frequency evolution, it's also only determined by the shear mass. So that's why it is the best constraint, because it's the parameter that controls the wave itself, how it is. Yeah. Yeah, so, right, so before actually going to the frequency evolution, what is important to notice as well is that actually here we are making a very specific choice of putting the observer perpendicular to the plane of the waves. So we have chosen this system, and we have put the observer up here. But in general, actually, the gravitational wave can have different inclination. So how does the signal look at different inclinations? Different inclinations. Well, actually, this is something which you can also check yourself, but it's a matter of just making a few rotations. So if you have our reference frame that we were using, X, Y, and Z, we can make a rotation of the Z axis by an angle theta, and then also we can make a rotation in the plane XY, which I'm gonna make, so that then we get a new, so this will be theta prime, sorry, this is X prime, this is Y prime, and then there is, I'm rotating by an angle theta and phi. So if you just take these two rotations to make any possible positions of the observer, so we rotate in phi, we rotate in theta, and rotation matrix are simple. You just have cosine phi, cosine theta, 0, minus sine theta, cosine phi, sorry, not theta, 0, 0, 0, 1. And then the other one, we do it in the Z direction, 0, 0, 0, cosine theta, sine theta, 0 minus sine theta, cosine theta. Anyhow, you can take this expression and then you multiply here, and what you're gonna get is actually that your gravitational wave, the plus polarization, is gonna be this expression that we already have. Let me write it again. G, shear mass to the 5/3, pi f to the 2/3, and then this has 1 plus cosine square of theta divided by 2, and then cosine of 2 pi f t times 2 times 5. And then for the cross, we have the same here. This is the same, but then here we have cosine of theta, and then we have sine of 2 pi ft times 2 phi. So what this is telling us is that actually the inclination angle, so what is the position of the observer, it's affecting the amplitude of each polarization in a different way. So we have one dependence here and a different dependence there. But actually, more importantly for the question of cosmology, what this is telling us is that if we cannot distinguish plus from cross, then actually our measurement of the distance is going to be degenerate with our measurement of the inclination. And this is actually one of the main sources of error when we measure distances with gravitational waves, because we cannot distinguish that well with our current network of detectors plus from cross, and then this carries an additional, yeah, there is a degeneracy that makes our errors a bit larger. Yes? Yes. No, so actually, and that's what I'm gonna explain in the remaining minutes. Actually, the signal itself, because the binary is emitting gravitational waves, actually it's losing energy. And if it loses energy, it's reduce its radius. And what this means is that the frequency is going to change as a function of time. It's going to increase because every time that it passes, it's going to orbit the black holes faster and faster. And then what I'm just going to write in a second is that actually this frequency evolution only depends on the shear mass. And therefore, from the frequency evolution, you get a measurement of the shear mass, and then from the amplitude, you get a measurement of distance degenerate with inclination. But very good question. Is there any other question related to that before I go to the chirp? Okay, so I don't have much time to do the derivation, but essentially the, yes, sorry, please. Well, it's because of the tensorial properties of the gravitational waves. Yeah, like changing the rotation in phi is just equivalent to changing the phase, while the rotation of the direction perpendicular to the plane of the waves change the amplitude. It's a consequence of the gravitational waves being perpendicular to the propagation direction. Yeah. Okay, so yeah, in the last minutes, but it's essentially what I have said by word, is that these signals actually, they are chirping. And this actually also relates to a comment that was made yesterday, which is that actually gravitational waves, they carry energy. And we don't have time in the course to derive this, but this energy of the gravitational waves is actually coming from the square of the perturbations. So this is the expression, and here there are some averages which are not. I don't have time to go into these details, but the main point is that gravitational waves carry energy. And then if you are emitting them, this energy needs to be extracted. So energy needs to be extracted from the orbit. And this is something that we know because we are always in the non-relativistic limit. So this is the energy of the orbit. This is the kinetic energy times the plus the potential energy. which is G, M1, M2, to R. And then what we see is that if you want to give energy to the gravitational waves, the way to give energy is to make this R smaller. Because if you make this R smaller, then you are making this larger. And that's what is sourcing the gravitational waves. But what one needs to do, and I'm not going to do the details of the calculation, is a good exercise that actually you could do, is you need to equate the variation of the gravitational wave energy with respect to time that comes from this expression, which actually already is very telling because it's an expression that only depends on the shear mass already. So that's, this is the, so if you take the solutions for the gravitational waves that we just derived, you take these time derivatives and you square them, you can get these expressions, and this is a G, the G Newton. So we have this expression, and then we want to equate this expression to minus the derivative of the orbital energy with respect to time, which comes from here. But then what we want to do is we want to re-express, you can re-express this expression in terms of the orbital frequency and the total mass. And actually what you can find, and this is again, is left for you to check, but that you get something which is, well, I'm 5 divided by 32. So here there are some weird numbers and powers, but the important element here, so this is what I've just done, is you plug this here, and then so you use that you can write the orbital frequency as minus G, M1, M2, omega S to the 2/3, 2 G to the 1/3, and then the total mass to the 1/3 as well. So I'm just changing R in terms of orbital frequency and total mass, and then I change orbital frequency in terms of gravitational wave frequency. But from here, we get to the final expression, which is very important as well, which tells us how the gravitational wave chirp. And that expression, which is going to be probably the last equation of today, this F dot is 96 divided by 5 pi to the 8/3. And then you have G, shear mass, to the 5/3. And then you have F to the 11/3. So this is actually an equation that, so what this is telling you is how the frequency is changing as a function of time. You see that it only depends on the shear mass, and it has also a simple expression that you can actually integrate if you want. You can integrate this expression to obtain the phase, but maybe more useful is to see how this frequency would look, and it's nothing but like an increase as a function of time. So, and this increase is determined by this power law here. So the signal is doing, so it's increasing the frequency, and then when you have that, and you look at the strain. So you see that the gravitational wave strain depends on the frequency. So if the frequency increases, the amplitude increases. So what's going to happen is that the gravitational wave is going to start to oscillate faster and faster, and is going to get a higher amplitude. So what I'm trying to do the best I can is to show that the amplitude increases and also that it's oscillating faster and faster. So this is the result, this is called the in-spiral phase. And that's the part that one can compute analytically, as we have just demonstrated, and tells you the behavior of the gravitational waves. And we have seen that this frequency evolution depends only on the shear mass, and therefore this allows us to obtain from here, actually, from the amplitude, we can get a measurement of the distance that is degenerate with the luminosity distance, with the inclination, but it gives us some direct measurement of the distance. So I haven't gone through the detailed calculation, but is this conceptually clear what I'm doing? Please? This one? Yes. Yes? Yes. So this is the, here both F's are the frequency of the gravitational wave itself. So yeah, it's kind of like a runaway process, like the more frequency you have, the more rapidly you are gonna change. Yes. So the one important thing here is that, of course, this calculation at some point stops to be valid, because we were assuming from the beginning that B over C was small. And then as you are moving faster and faster, orbiting faster and faster, that's going to be broken at some point. So actually, the part that we cannot, so this is the in-spiral, this is the part that you can derive analytically. We have done the very leading contribution. There is a lot of people actually who have made like heroic efforts to compute higher order terms to this, because you can compute a lot of terms that go beyond the quadrupolar term and higher order in the expansion. But inevitably, at some point, you will always reach a case in which your system really cannot solve analytically. And that's the part which is the region near the merger that needs to be studied numerically and needs to. So this part of the spiral is when the binaries are relatively far away. When they are almost touching with each other, one needs to use numerical relativity. And then once you have a single black hole that is perturbed, actually this part is called the ring down. And this is something that I don't have time to go in the course, but actually you can again compute analytically. But this part here in between requires numerical relativity, and it's just because at some point the black holes or the neutron stars, they are moving so fast, space-time is so non-linear that all the approximation we've made, they will be broken. Yes, please. Well, actually, it's actually quite important because most of our signals that we detect, we only see the signal close to the merger. So actually, the data itself is mostly just a few cycles before the merger and then the ring down. So then all your information is coming from there. If you have something that I should, this is very important. So what you get from this expression also is that if you have if you invert this expression, you can compute the time that it takes for a signal to merge. And actually what you find is that the time that it takes for a signal to merge is inversely proportional to the shear mass. So for a given frequency. So what this means is that systems which are lower mass, they are much longer time in our detectors. We see a lot of cycles. And signals which are higher mass, we only see a few cycles. You can also see here that the frequency of the chirp scales with the inverse. So the lower mass, the higher frequency for the chirp, and then you observe this for longer. But we observe most of the signals to actually be tens of solar masses, and those only are a fraction of a second. So the merger is very important. I see that you already stand up. I see that it's time to close, but yeah, I don't know if there are more questions. Yes, please.
Hi, Professor. I have a question. Is the chip mass will evolve with the time or not? The chip mass?
No, so the shear mass is a fixed quantity.
Okay.
So the shear mass is defined by the masses of your binary.
Yeah, but the binary, when they evolving, then the mass will change or not?
No, the mass does not change. What it changes is the frequency, how fast they are orbiting.
Okay, but I see some maybe black hole when they evolve, then the mass will change.
No, so the mass of the components does not change, but actually, if you take the mass of the components as you add it up, and then you look at the mass of the remnant black holes, they don't match with each other. And that's because part of the energy, like about 1% of the energy, is released in gravitational waves. So there is some conversion of mass into gravitational waves, but during the spiral, you can consider the masses to be constant.
Okay, thanks, Professor.
Yeah, well, yes.
Yes.
That's an advanced point.
This part of the ring down, if I understand,
Yes.
you will solve the wave equation, but not the wave equation of this class, the wave equation from last class, where you have the Riemann tensor and the box was with the...
Exactly. So the equation that we had for the last class, that if you solve this in a strong gravity for a black hole that has been perturbed, you can find solutions for that. Yes, and that's how you obtain the ring down.
But on the left side, on the right side, you can no longer treat the compact objects as point objects.
No, exactly. That's exactly. You are seeing the horizon because you are seeing a strong gravity, so you see the horizon of the black hole.
How would you more or less do the?
So that's a whole other course. So if you see the notes from the course that we have at the Niels Bohr, half of the course is like black hole perturbation theory. I do the other half, but it's actually it requires a lot of work.
Okay.
So it's not easy to say now. Yes.
Okay.
But you can have a look if you want.
Yes. Thanks.
Thank you, Jose. Perhaps you could comment on another way to see these things is look into the binary. In the case of the pulsar binary that gave the Nobel Prize
Yes.
to Hussein Taylor. So if this thing gives the effect that the period of the pulsar gets smaller and smaller and smaller, and then there's an indication that there is some gravitational waves coming out from it, right? So what's the first indication? Of
Yes, yes. Yeah, thank you for that. Actually, that's a very good point that I should have mentioned, that the first indirect evidence for gravitational wave was actually from observing how the orbit was shrinking, and that was that was following all these laws. Yeah.
Right. I don't know if you finished your lecture, but I have a. I don't know if
Yes,
that's,
I'm done.
Okay. I don't know if it's a silly question, but can you actually, from the spiral phase, differentiate which kind of compact objects is the thing that you are seeing?
So at this level of approximation, which is the most basic you can do, we have point masses, so you don't distinguish.
Right.
You need to include you need to go beyond that, and then you can get corrections, and in particular there is the tidal deformability that tells you how much conceptually you can deform the objects, and then as you are the compact objects are getting closer, actually the signal starts to become sensitive to these deformations of the shape. But it's a small signal until quite close to the merger. And in fact, from the observations that we have of binary neutron stars, we have some measurement, but it's not like outstanding yet. So it's because it takes some time for it to appear. But yeah, there is an effect there.
Right. Thank you.
No, I think sorry. No, I'm done with the lectures. I'm just yes. Maybe just one thing, that the exercise that I added to the in the GitHub repository, it's about computing this signal, but in frequency domain, and that's essentially just doing the Fourier transform of this signal, and that's useful because when you do data analysis, actually working in Fourier space is useful. So if you have time, it's a good exercise to do. Yeah, thank you. Yes. No, it's true that of course the nonlinear effects, you absorb the waves and then but maybe she was referring to that. I was not sure if.